All right, I'm starting to record this lecture now. Let me share my screen on the lecture slide while waiting for your other friends. So I believe that you have already gone through the lecture just now. This is relatively a shorter lectures where you'll be introduced to Laplace transform. So since you have already gone through the lectures, I'll just brief through some of the important points here. And if there's any questions on any slide, you can just stop me. Either you just voice out or you can just post on the group chat. I will be monitoring the group chat as well. So today you will be introduced to Laplace transform. And what is it so significant about these Laplace transforms is that there was a very tight limitations on Fourier transform. Remember, in Fourier transform, if I draw the graph over here, your time domain signal need to be closed on both ends, meaning that it has to go to zero when either time is very early or at times is very late, like at infinity. Because what basically Fourier transform does is that it takes an integration of that signal. And integrations meanings the area under the graph. Hold on, let me let Brian in. So to take area under the graph, you cannot have a graph that is open-ended. So for example, if your particular graph, if your particular signals behave like this, then it is not possible for you to take integrations of this signal because the integration, which is the area under the graph, will be infinity. All right, so therefore, Laplace transform help us to solve this problem. But however, because of the nature of the Laplace transform, after you do the transformations, you no longer obtain the correct amplitude in the frequency domain. So Laplace transform actually does not, the motivation of Laplace transform is not for you to work your signals or to see your signals in frequency domain. If you want to see the frequency component of your signals, you have to use Fourier transform. So Laplace transform has other purposes. So it's kind of like converting a signals from time domain into another domain, which they call it the S domain because it's the Laplace domain, S domain. And then by converting it to S domain, certain operation that is quite difficult to carry out in time domain can be done easily within S domain itself. So let us look at how Laplace transform able to transform a signals into S domain, even though the signals has open-ended, for example, signals like this. So what this Laplace do is that instead of just integrating it over e power to negative j omega t, it also try to suppress the signal by multiplying to something called e power to j gamma, j sigma, sorry. Let me let Kim Long in. So this Laplace transform has an additional terms of e to the power of negative sigma. So if you plot the e to the power of negative sigma graph out, it looks like this. So e power of negative sigma will start from 1. All right, so let's say this one is the time axis. This is when time equals to 0. It starts from 1, and then it will slowly suppress when time is greater. Let's say when time is near to infinity, this value will go to 0. So it kind of like suppress the variable signal that was, for example, the red color signals over here. So when you multiply both the signal together, you get the green color signals, which I will draw now. You get a signals that looks like this. Therefore, now you'll be able to find out the integrations of that signals multiplied by e power of negative sigma, and you have a finite value because it will be close-ended now for this signal. So that is the motivations of Laplace transform, where you add in one more term, e power to negative sigma. So they close it together. This is what I explained. They put it up together as e power of negative st. So this is basically e power of negative sigma t multiplied by e power of negative j omega t. All right. So now, if you look at the e to power of j omega t, where is the equation? Okay, the equation is not here. All right. If you expand this out, infinity from negative infinity to positive infinity, you get xt e power of negative sigma t multiplied by e power of negative j omega t and dt. And you'll notice that this part, if you close them together, if you multiply them already in your graph, it's kind of like a new graph, a new signals, and you do the Fourier transform on the new signal, because all the rest of the equations are exactly the same, except that now the signal is being suppressed by e power of negative sigma t. So in Laplace transform, there's one very important concept, is the concept of regions of convergence. Later on, you will learn about this ROC. So this ROC stated that there is a certain value or certain range of sigma that can make this graph really suppressed down. Because let's say if my graph, the original xt looks like this, and my e power of negative sigma t, it should be suppressing, so it should go down, looks like that. But if this particular rising up is rising up faster than the suppressing, then the overall graph will still be rising up. You see, the overall graph will not be suppressed. So there is a concept called region of convergence, where we need to calculate the value for sigma so that this whole green color signals will get suppressed. All right. So let us try.
Which domain will be the Laplace transform?
Okay, Laplace transform will transform into a special domain. You can see it like frequency domain, but it's not really frequency. Like I said, the frequency information actually has already lost, because you multiply, you suppress the signal already. All the amplitudes are suppressed. So we usually just call it the S domain. So you can treat like a new domain similar to frequency, but you will not need to plot frequency spectrum anymore. In Laplace, you never plot frequency spectrum. Okay, so it's a special domain by itself. It's called S domain. And then this Laplace was actually developed by, well, this guy named Laplace, but his story is quite sad. Not really sad, but after he developed this Laplace transform, people think that it's quite useless. So nobody ever thought about using Laplace transform for anything until later, about maybe 50 years after he has died, or more than that. I think 70 or 80 years after Laplace has died, this fellow, Olivier Heaviside, has actually found out that some usefulness on Laplace transform, which you will learn in this lecture. Okay, so it is actually promoted by this guy, the Heaviside. So Laplace never get the fame when he was alive, but he get the fame after he's dead. All right, this is what I mentioned earlier on the integration. So like I said, this become a new signal, a suppressed signal. And then you are basically working to get the Fourier transform of a suppressed signal. All right, so what is so good about Laplace transform? There's people has actually found out that Laplace transform works very well on ordinary differential equations or partial differential equations. So I give an examples here. Let's say x dot t plus 2xt equals to yt. Let's say this is a very classical first order ordinary differential equation. I want you to find out what is xt. All right, in this case, or what is yt in this case, without the differentials. So in order to solve the ordinary differential equations, the usual way involve very heavy mathematics. However, if we apply Laplace transform, what we need to do is that we need to transform this particular differential equations into Laplace domain or into S domain. And you will notice that in S domain, all the derivative become algebra. So if you have x dot t, it will become s. If you have x double dot t, it will become s squared. So in the end, it becomes solving polynomial problem. So if you solve the polynomial and then you get the solution, then you apply inverse Laplace. And there, people have found out that that solutions, after you apply the inverse Laplace, is exactly the solutions for doing the ordinary differential equation. So you skip all the difficult mathematics. What you need to do is just transform it, solve polynomial, and then inverse transform it. So this is the formulas for Laplace and also the inverse Laplace. As usual, just like the Fourier transform and Fourier transform and discrete time Fourier transform, people has constructed a Laplace table that you can refer to for most of the systems. So in today's lecture and also in this week tutorials, I would like you to do your Laplace from integration first. Then for next week lectures or any other lectures onwards, you can refer to the tables. Like even for the quiz, quiz is open book, it's just ABC. So it doesn't matter what methods you use. Even for your, let's say your final project, final case study, you can just refer to the table if you can find it on the table. But for this week tutorials, I'll request you to do from integration, only for this week tutorial, for you to get familiarized with Laplace transform. So inverse Laplace transform is given by this formula. It's very similar again to the inverse Fourier transform. Basically, it's just replacing all the j omega into s from Fourier transform into Laplace transform. All right. So just now I was saying that regions of convergence is very important because our motivation of Laplace is to suppress the signal. But if the signals is so large that you cannot really suppress, it's not saying you cannot really suppress. Definitely, there is a value for you to suppress it. Just that you might need to find a suitable regions for this gamma, for this sigma, so that the whole things will be suppressed. So what do I mean by that? Let us look at one example. If you have this particular signal, so this signal, if I draw it out, there is two ways to draw this signal. This is a time domain signal. The first way, okay, is starting off from 0. And from here, the first way is that it goes from 1 and then suppress all the way. That is E negative AT, correct? And then because you multiply by UT, therefore it only starts at time t equals to 0. This is 1. However, if your A is negative number, your signal no longer looks like this. If your A is negative number, your signal will look like this instead. It will go to infinity. This is when E negative AT, where A is negative number. So what we need to do is that when we substitute the whole equations into the Laplace transform, you will see that for this particular example, these two E can be combined together. Negative A plus ST. we need to make sure that this E negative A plus ST does not behave like this. Meaning that we want to make sure that A plus S is always greater than 0, correct? Because when A plus S is greater than 0, the whole thing is a negative exponential curve. So your curve will look like the green line now. It will suppress down, so you can find its area. So this one with the condition of A plus S must be greater than 0. So like I said earlier, S is actually having a real part and imaginary parts. These are the real parts. So to find it greater than 0, we ignore the imaginary parts. We only care about the real parts. So the real parts of A plus S must be greater than 0. So the real parts of S must be greater than negative A. So basically, you just treat S like a real number. You just S plus A must be greater than 0, so S must be greater than negative A. And then you add a real in front, right? Just treat it like a normal algebra. So this tells us that when the real part of S is greater than negative A, no matter what value of A is, this signal is being suppressed. So you can find the area of this signal under the graph, the area under the graph here. So that is this particular range, we call it the regions of convergence. And most of the time, you will need to plot out your regions of convergence. But for this case, because this is just real numbers, a single number, so we can just plot it this way. This is negative A, and then S must be greater than negative A. So you can just use an arrow to represent it. Or if you want to use area to represent it, up to you. Why do I ask you to draw it out? In the tutorial, you'll notice later, I'll ask you to draw out the regions of convergence. That is because later on when you study Z transform, in the next topic, not Laplace transform, but Z transform, you will notice that Z transform region of convergence are actually circle. So when you draw it out, it's better visualization, it's a circle. So for Laplace transform, your region of convergence is always a straight line. Z transform is always a circle. So when you draw it out, you can differentiate them. All right, so now this example. So it says, find the functions, these particular functions in S domain, meaning that we are going to find the Laplace transform. So we need to integrate, and this signal is 1, multiplied by e power negative st and dt. And because it is only happen when time t greater than 0, so our limit is 0 to infinity. And then this integration can be done easily, right? But there is one condition. This integration only valid when your S is greater than 0, correct? Because it is only valid when this is negative st. So your S must be greater than 0. Your S cannot be negative number. Or else, later on, when you substitute this is here. When you substitute infinity into your equation, if your S is a negative number, meaning that this will be e power to infinity, which gives us infinity, then you wouldn't find your Laplace transform anymore. So this is not ended yet. You need to write here regions of convergence. At this particular example, when you find the Laplace transform, is real parts of S must be greater than 0. All right, then only you can get this 1 over S as your Laplace transform. So I have another example here, which has a lots of different sub-examples. So it is similar, where you just need to substitute one by one. We start from e power to 1, e power to negative t, and then you do the integrations. Your integrations will look like this. Later on, I will let you know why most of our functions are e power of negative t are in this format. Later on, maybe in the next lecture, because most of the systems are actually behaving this way. All right, so back to our topic. if you substitute infinity to it, you need to make sure this s plus n must be greater than 0. So real part of s plus n must be greater than 0. So real part of s must be greater than negative n. Right? So this one means that the real part of s must be greater than negative 1. This real part of s must be greater than negative 7. And so on and so forth. This is positive 7 and this positive 8. All right? For the Laplace transform to be valid. Right? Remember, regions of convergence is a regions where your Laplace transform is valid to apply on that particular signal or systems. And we have several properties on Laplace transform, like I mentioned earlier as well. It's very similar to Fourier transform. It's exactly the same, I can say, because both are integrated through the e power of j omega t here. Although Laplace, you have additional sigma t, but that just suppresses the signal. There's nothing much difference. So all the properties are same, linearities. You have homogeneity and additivity. So this one is additivity and this one is homogeneity. And then time shifting is also a very important concept, where if you have shift in time domain, in S domain is just multiplied by e power of negative s, and then the shifted time t. You can apply this in your next tutorial, these tutorials that we will discuss on Friday. Frequency shifting. So for frequency shifting, it's just the opposite of your time shifting. You can see that when your S frequency shifted by certain amount of time, it means that your time signals multiply by e power of s, that amount of time multiplied by t itself. Okay, so this is same. Time scaling, time reversals, they are both the same, and differentiation in time domain. Okay, so now if you have x differentiations in time domain, when you Laplace it is sxs. All right. Actually, there are more things that you need to see. Let me check where is the differentiation. I'll talk more about the differentiation things. There's also initial condition you need to take care. If you look at convolutions also, when you have convolutions in time domain, is multiplications in S domain. Oh, for the first lecture, that's it. Okay, so more. Okay, I said that I wanted to tell you about this thing, right? There are more of them. This actually has another things called the initial conditions. There is an x0 here, but in most of the cases, we assume initial conditions is 0. So this one will be 0. All right. In the next lecture, you actually learn it. I thought you will be learning in this lecture, but no. This lecture is just introductions to Laplace transform. That is why it is quite rather straightforward and simple. So anyone has any problems with this lecture?
Sir.
Yes. Kinlong.
Want to ask more about the ROC. First is how we actually, where do we look for the part that is less than 0? Because I have did tutorial, right, and I feel like it's kind of weird.
Okay. The ROC is to ensure that the integrations can be done. So in this particular, I don't have example here, but let me take this as example. In this example, I have to integrate 0 to infinity e power of negative st dt, correct? Yes. And then in order, okay, that this integration will come to this one.
Yeah. Okay.
And then now I need to substitute t equals to infinity and t equals to 0. Is that correct?
Yeah.
So
okay.
I need to substitute this e negative s infinity minus e negative s 0. And you notice that whatever substitute with zeros, this one will always be 1. But this thing that substitute with infinity is either e positive infinity or e negative infinity, correct?
Yes.
It depends on s. So we need to make sure that this will happen. Because if e positive infinity happens, this whole thing will be infinity. You get no answer. So we need to ensure that negative infinity happens. So for this case, how do you ensure negative infinity happens? By looking at this. So negative s must be negative number, correct?
Yeah.
Or I can just say s
must
be greater than 0. Like I say, s has a omega, sigma and j omega has two things, real and imaginary. So we just need the real part to be greater than 0. That's all. Right? The imaginary part will not play a role here.
So when we actually look for the ROC, we actually look for a real part from negative s, or maybe there's s plus a. If there's a case.
If you have s a here, okay, let me find one examples from here. Okay, I think I take one of this example. Okay, let's say I take this, for example, n equals to negative 7. So I have ft equals to 3e 7t. All right, now you see it's positive now because n is negative number. So when I do integration,
okay,
when I do integrations, because this one is t greater than 0, so again from 0 to infinity is 3e 7t e negative st dt. So I can group them together. I write it at the bottom here. 3 I just pull out because 3 is just a constant. This become e 7 minus s t dt. And so when I do the integrations, I get e 7 minus s t divided by 7 minus s. All right, and then it go from 0 to infinity. All right, 7 minus s I can pull out first. So this one is 3 over 7 minus s. And then I have this e 7 minus st that goes from 0 to infinity. And now you see, like I said earlier, I ignore the 7 over s, so I should write this part over here. So this become e 7 minus s infinity minus 1, correct?
Oh yeah.
Yeah, but then the thing is here, we cannot, this e 7 minus s is either e infinity or e negative infinity. We want it to happen this way. The region of convergence is when e power to negative infinity, so that this will become 0. So we must have 7 minus s, or you can just write real parts of 7 minus s must be smaller than 0. Because it will only go to negative infinity when 7 minus s is a negative number. So it must be smaller than 0. So for this one,
You're actually not looking from the part after integrate, is it?
yes.
Because I thought it was looking from the negative at bracket s plus n that part.
Which part? You mean this part?
No, I mean the blue one. Okay, it's 3 a square bracket of e power of negative s plus n bracket t, right? I thought it's looking from here.
This one, is it?
Is it? Yeah.
It's the same. It's the same. Because I just substitute it into it. You look at from which one also similar. So as long as I need to make sure that this this particular case, s plus n must be greater than 0. Because I have a negative number, I have a negative sign here.
Okay.
Right, then that's it. So s must be greater than n. And like I said earlier, you just put a real sign in front.
Sir, then is it possible that we look at tutorial 1?
Tutorial 1.
Sorry, tutorial 7, question 1.
Yeah,
Because
okay.
I've done that and I actually getting a weird A.
Okay, we'll only discuss that questions for now, so that you guys can continue doing the other question using the similar way. So I'll open up my tutorial. Give me a moment. All right, this one, is it?
Yes, for first question.
Okay, so for these particular questions, we want to find out the Laplace transform. So it's xs will be equals to infinity to negative infinity, negative e, negative at, and then u negative t, and then e negative st dt, correct?
Yes.
And now there are a few things that we can do. First thing, I don't like the negative in front of e, so I pull it out. Then the second thing, this is a u negative t signal. U negative t signals is like this, at 0. So wherever from negative infinity to 0, there is something. Wherever after 0, there's nothing. So our integrations is actually from negative infinity to 0. That is because of u negative t. All right, this question is a tricky question because I write negative t here. Okay, so the integration will be 0 to negative infinity. Then I just rewrite the whole thing. Negative a plus st dt. Now I need to do the integration. This become e negative a plus st divided by negative a plus s. And then from negative infinity to 0. So this both cancel out. So it becomes 1 over s plus a e negative a plus s t. Hold on. 0 to negative infinity. And now I substitute it into it. 1 over s plus a. This is e power to 0 minus e power to negative a plus s negative infinity. Now you see there are two negatives, so these two negatives actually cancel one another. All right. Now you should know how to do already, right?
But sir, e power of infinity is infinity though.
Yeah, but then we can make it negative infinity, correct? Can we?
Okay.
You see, when a plus s smaller than 0, then this is negative infinity.
Oh, okay.
Yeah, so your regions of convergence is actually this. A plus s must be smaller than 0, so s must be smaller than negative a. Then you add a real in front. Okay?
Okay, so this is for ROC, but if we continue doing the integration, what are we supposed to put for e power of, oh, we just assume it as e power of negative infinity?
Yeah, because we already say that it only validates when you have this condition satisfied. So this thing becomes 0. This thing becomes 0. This is 1. So your answer is 1 over s plus a.
Okay,
so you use similar methods to try. I want everyone to try the tutorial, okay? Don't just wait for my answer. So, is there any other participant coming? Oh, Muhammad Humai is not here, right? I don't see him. Okay, it's okay. So that is all for the lecture today. We will talk about tutorial on Friday. Yes, so that you have time to do after your lecture. That is also one reason Dr. Aravind thinks that it's better to do not as in lectures on lectures